Okay, next speaker on this morning is Elisa RESCONI from the Technical University in Munich. Elisa is going to speak about neutrino astronomy in the multi-messenger era.
Okay, so good morning, everyone. Can you hear me? Yeah, okay, I was not hearing me. I would like, first of all, to thank the organizer for inviting me here. It's a great honor to be among such a great speaker talking about neutrino astronomy in the context of multi-messenger. So I'm going to start a little bit from the beginning. So Razmik already covered quite a lot about cosmic engines, so machines that are able to produce cosmic rays, gamma rays, and neutrinos. This is, of course, very broad, so I'm going to focus on extragalactic scenarios and pushing to the ultra-high energies in all these three messengers. I will more or less stay observationally driven, and not because theories are not doing a good job, it's only because, as I will stress in a second, there are so many theoretical questions still open in all this business, and we really need data to give us a hint where to look and where to work a little bit more intensively. I will then come to the Blazar case, and then, as already Razmi anticipated, game two, some elements of what I like to call a game changer is connected to one IceCube event. We cannot tell much, so next week you will hear much more, and for sure from Francis too. Okay, so once we talk about cosmic accelerators, indeed we think and we work around quite a lot of different materials. So I divided the working blocks in three. Number one, everything that we think we work around concern acceleration. Acceleration essentially of electrons and protons in environments that by today we don't really know very well. Of course, Fermi shock acceleration is one of the mechanisms, but once we go in the direction of trying to address 10 to the 20 electron volt protons, then we need, if we stick to this idea, such an extreme environment that one starts to doubt that maybe is the full story. So one alternative, and I don't cover that because number one, I'm not an expert, but I think I'm very fascinated from this work, is that the particle can be boosted through also Wakefield, plasma Wakefield mechanism, and this is a paper where also cosmic ray up to 10 to the 20 electron volt are determined through such a mechanism. Okay, so acceleration for us means we assume, so we don't even calculate sometimes, or most of the time, we assume primary spectra, primary electron, primary protons, and then what eventually is calculated, at least in some form and in different fashions, is what these primary particles will do in the environments where they are accelerated. This is all relatively known physics, and this is concerned the electromagnetic part of all of this. And the only maybe element, if you're not an expert already and you know already all about that, to keep in mind is that if we have not only electrons, but also protons in the game, then eventually protons will interact with the target photons to a certain extent and produce secondaries. And the secondaries will be neutrons, will be able to escape as neutral particles and produce then probably the primary cosmic rays that we measure in Auger, telescope array, and so on, and neutrinos. Moreover, connected to this, we also expect photons that on top of the inverse Compton photons will come with a signature that should be, by construction, very similar to the neutrinos. So once we look into neutrinos, we look also for twin photons that should sort of come to a certain similar energy scale and similar spectra or things like this. Okay? So this is block number 2. And block number 3 is basically once our messenger succeed to escape the acceleration and the interaction regions in whatever fashion, and they propagate. And also the propagation through the cosmos is completely different. So the horizon for these three messengers are totally different. So every time we try to combine all of this, it's nearly impossible to take into account all these elements. So cosmic rays in their charge part, they will deviate slightly from the intervening magnetic field, slightly, of course, depending on the charge, depending on the energy, and so on. They will also absorb through different mechanisms, again, depending on the energy. So the horizon in primary cosmic rays is not that large. Photons, they are not deviated, of course, but also they are absorbed to a certain extent. And so in particular, above the TeV scale, the universe is not transparent to these photons anymore. So their horizon is also not infinite. And then we come to the neutrinos that, in principle, they are, of course, not deviated, and they travel straight at whatever energy you want through the universe. So in principle, they are the ideal messenger, despite that to detect them is really extremely difficult, and that's the reason why we need this huge neutrino telescope like IceCube to start to see cosmic neutrinos. So what I always wish to have is a face for every messenger. And so coming here, I was super happy because today I think we have faces for every messenger. So Ralph will cover the cosmic rays after the coffee break. Francis after me, the neutrinos, and Razmi already cover the photons. So it is this part of multi-messenger is perfectly covered today. And so my role here would be simply to try to bridge among the three. And as I said, I will do it data-oriented, taking Pierre Auger and telescope array data together with IceCube data, together with essentially Fermi. Razmi already has covered the Cherenkov telescope, but since the Cherenkov telescope are pointing experiment, and these guys are, let's say, a survey experiment covering half the sky or the entire sky, Fermi is an ideal partner for some of the things we do. Okay, so then let's jump into the data. And let's start with the photon sky. And the photon sky is a fantastic cover since 10 years by Fermi. So Fermi revealed a huge amount of information. There has been a session about this. And I just pick up one picture. This picture is the high energy all sky in galactic coordinates. So if you just exclude for a moment the galactic plane, you might get the impression that there are a number of different objects in the extragalactic sky. In reality, if you would then read the labels, you will find that all these different dots and different colors and different symbols, they tell you one fundamental message. And the message is the entire extragalactic sky at high energy is dominated by one category of source, and these are the blazar. Blazar by now are listed and cataloged in different fashions. So the literature is relatively rich. It's a field that evolved, from the 90s, and here we have the word expert around me, so I have to be very careful what I'm saying about that. But what I wanted to say is that observationally, we are approaching the 4,000 objects detected up there. So for the few that maybe don't know what a blazar is, let me remind you that these are active galactic nuclei with the jet towards us. Okay, so they are the lighthouses in the universe. So it's not a sort of surprise that these are indeed the site of the major emission at high energy. They are typically characterized by a very broad band emission that comes with a standard shape of a double hump. And let's say the main characteristics for distinguishes them is the first hump, and in particular where it peaks. The first hump are photons coming from synchrotron radiation, and so depending where this peak peaks, then blazars are classified in different fashion, low frequency, intermediate, and high frequency blazar. Then we have the flat spectrum of the quasar and the BLAC, depending if there is a disk or not a disk, and so on and so forth. But in first approximation, you can just keep in mind the synchrotron peak, and then, of course, depending where this guy peaks, then the second hump, which is the high energy part, which could also have some photons coming from the hadronic interaction, and so the twins to the neutrinos, peaks, right? So progressively they move. Right, so then we have let's say, painted a picture. So the picture contained essentially blazar in the high-energy sky. So what about the neutrinos? Are we starting to see them? So IceCube will be then covered by Francis. So I jump into the data. I remind you essentially that IceCube has two signatures for detecting neutrinos. One is about, we call it track, so basically muon type of neutrinos interacting around the detector produce a leading muon, and the muon leave a fantastic track of Cherenkov that the IceCube detect. So these track-like events are very useful for searching for sources because they point back, and at high energy they point back reasonably well in a fraction of a degree. So we have collected by now 500,000 of neutrinos, but not cosmic neutrinos. These are mainly atmospheric neutrinos. IceCube has been detecting cosmic neutrinos, so unknown atmospheric neutrinos since 2013, but by today they are still diffuse. And so once we look into maps like these, when we collect from, let's say, some 100 of GeV up to the PeV neutrinos, every dot in the sky is still compatible with background fluctuation. So don't get it wrong. All these blobs are not neutrino sources, are fluctuation of the background. This happens once we look into neutrinos as in the vacuum somehow, without thinking or without taking into account what actually astronomy is telling us. So if we look only, let's say, unbiased or model-free or assumption-free the neutrino sky, we have to pay a huge penalty, statistical penalty, because every dot in the sky is identical to everyone. And so basically, maybe some of these fluctuations actually come from a source, but without hypothesis coming from astrophysics, we might not able to resolve these dots in the sky. We can then use the second signature. These are blobbish type of events, shower-like events that are produced within IceCube to certain statistics once electron neutrino or tau neutrino or neutral current interaction happens at high energy in the detector. And as you see immediately, these areas are actually the angular uncertainty associated to each neutrino. And so if you now shake your head, I will understand you, because this implies that the pointing, in this case, is really horrible. But the good thing is that once we identify these events, for a high majority, these are actually cosmic neutrinos. So to a certain extent, our golden event in terms of energy spectrum, but the point is too weak to start to at least see statistically significant accumulation. Again, provided that we don't take into account anything from gamma ray astronomy or from primary cosmic rays. So let's go to the primary cosmic rays. This is the combined map of telescope array and Auger, modulo that these two telescopes don't have the same exposure, so Auger is much larger than telescope array. And I don't enter because Ralph will cover all of this, but one message I think I want to bring over, which is very important and significant. So the sky in primary cosmic ray is not isotropic anymore. And with that, I fold in a lot of stuff, including large-scale anisotropy, medium-scale anisotropy, and so on. And the fact that it's not isotropic or perfectly isotropic anymore is a good news, because that is the first step to basically approach the main question about the origin of this particle. Good. Another way to look into essentially the same data is to put them on an energy spectrum. And this is the energy flux versus energy, the Fermi data, the IceCube, diffuse neutrinos, and the ultra-high energy cosmic ray. As I told you, these three windows, right, are basically independent, right? These are different instruments with different exposure, with different systematic, with different everything. But once we had started to do this type of plots a few years ago, essentially the first observation was, interestingly enough, they are all cutting at the same order of magnitude in energy flux. Might be a coincidence, or might be a first thing that suggests that to a certain extent these three messengers share a common origin. And so if you allow me to go on in this speculation, And if you remind what I just said, if this common origin should be somehow imprinted, what could be else than Blazar? Because eventually, as Fermi and also the people here in the audience told us, this diffuse component is dominating, in particular, the high energy from Blazar. And so with Paolo Padovani and Paolo Giombi and colleagues, Apostolo Mastichiadis and Maria Petropoulo, we have been then bridging the photons to the neutrinos, and I come to that in a few details in a second. So before coming to the diffuse, I want then to answer a possible question that maybe in your mind now is sticking, and say, are actually Blazar good possible candidate sources for neutrinos, right? Because the environment is extreme. They are accelerators, they are non-thermal, but are they actually good also proton accelerators? Of course, today we don't know yet, but we can work with people and trying to, for example, interpret the spectral energy distribution of single objects. And what we have been doing, again, with Apostolo and Maria Petropoulo, is to run an electron-hadronic model, their electron-hadronic model, on existing SED. And interestingly enough, once you combine the leptonic and the hadronic energy losses and interaction, you could find parameter spaces, so values in the parameter space, that will allow a neutrino production. This is the neutrino signal, which will be decently enough, sizable enough to basically be seen by IceCube. So IceCube can, in principle, see neutrinos from Blazar, including the high-frequency Blazar. And this paper somehow had the goal to demonstrate that with the state-of-the-art electron-hadronic model, in principle, this is possible. This is possible in IceCube today. So, but before entering in the single source, then let's do what we could with the data that we have. Namely, we know the Blazar population. Giombi and Padovani have a full machinery. It's called Blazar simplified view that I think is a little bit misleading because simplified maybe somehow tell you that it's simple. Actually, it's not that simple, but I think it tells you that it's simpler with respect to what was before, and actually it is under control. And so with this machinery, you can reproduce everything, radio, X-ray, gamma ray, and plugging in an assumption on the hadronic part, you can also estimate a possible neutrino signal. And interestingly enough, that is what we did. These are the IceCube data. This is already a couple of years old, but nothing spectacularly changed on that. And these are the prediction. Of course, you see the parameter space is huge. We don't know how many protons are active in these sources. So there is a lot of assumption in this game. But what is appear is that if we calculate all of this, the diffuse will be coming with a relatively hard component and will enter in the signal of IceCube at relatively high energy. So it's not able to explain everything. So Blazar might be able to explain a fraction. If this fraction is the high energy part or the intermediate part, who knows, right, today. But the good news is, again, the signal of the Blazar could be imprinted in the IceCube cosmic neutrinos already. All right, so now I hope that I could create some expectation in you and say, okay, what IceCube data are telling us? Are the Blazar there? Not yet, but maybe. So that is the worst situation ever, right? So I start from the not yet, so from the upper limits. So once we have this fantastic 500,000 events and we don't see any point source, then we can calculate upper limits. So the upper limits that you see here from the entire sky, this is the horizon, this is the north, and this is the south. We are better in the north with respect to the south. We can also translate them in single sources. And here maybe it's a little bit tricky. You can concentrate just on the blue lines. So the blue line is a prediction for the Markarian 121, and the blue line with the arrows is the present upper limit from IceCube. And once the upper limit is below the expectation, you start to be happy because essentially you have started to constraining, not excluding, but constraining a possible hadronic component, at least following a specific model. You are happy not because you are constraining. You are happy because you get the feeling that you can start to detect them soon. So IceCube is at the discovery level for this type of source, but only for few, for the brighter one, okay? So you have here other example where the upper limit is still nearly 1 order of magnitude far from the prediction, from the optimal and optimistic prediction. We have done, of course, stacked the existing catalogs, okay? The second FHL, the second WHSP, the third LAC, the 3 FHL is still inside IceCube, and you see here all the different catalogs and equatorial coordinates. Basically, we sum all the neutrinos from these spots, and we hope that then we start to see more neutrinos from Blazer, for example, from a specific category of Blazer, respect all the others. And well, to give you a short answer, for the moment, the stack is not giving us a hint that Blazer are producing more neutrinos. And so, again, we place upper limit. And for the stacking upper limits, even more important to respect all other upper limits that we produce, I have to remind you the upper limits are based on a number of specific assumptions. And so once we place upper limits, they are always related only to these specific assumptions. If you change the spectrum, if you change the weighting, if we change anything else, these upper limits are going to be irrelevant. And I give you here 2 examples that are quite extreme. This is, again, the diffuse emission of cosmic neutrino that IceCube measure. And if we assume that all the Blazer are having a specific spectrum, a steep falling 2.13, 2.5, or so on, over different orders of magnitude, and we sum them up, well, we can constrain quite a lot the component of Blazer respect the diffuse. But it's enough to change this assumption to another assumption, which is a little bit more physical motivated, by the way. So spectra like Mario Petropoulos has been provided us. And then once we plug in this different assumption, and the upper limits also relax quite a lot. And here we can still have about 30% of the diffuse emission produced by Blazer. And again, if you produce another assumption, I bet this would be another constraint. So don't take all of this very seriously. The message is simply that we can somehow investigate each single case you might have, and we are happy to get any input for satisfying curiosity, but don't try to extrapolate from what we calculated a specific upper limit to your specific model. All right, so then to basically continue this hunt and this investigation, we have tried to invent, to make sense out of the data that we have. And another technique we have been developing, we have been calling neutrino filter. Essentially, using the cosmic neutrinos from IceCube, we have been filtering out existing catalog. So the filter for the moment is very simple, it's 0 or 1. So 0 every time that there is no neutrino, so the sources, the Fermi sources that are not in spatial connection with a neutrino are not basically put it in a subcatalog, and the ones that are in space connection are put in the second subcatalog. And so we have from one catalog 2 subcatalogs, and we use these 2 subcatalogs to correlate them to cosmic rays, okay? Of course, you can find immediately 100 questions, and you might ask what is legitimate or not, because we don't even assume an horizon, a different horizon from cosmic ray to neutrino to photon. As I told you at the beginning, the horizons are different. But then once you start to ask yourself which horizon you want to plug in, you are stuck in so many questions that eventually we thought we are minimalistic in our approach. We don't assume anything, and we just look if the data somehow indicate one or another option. Again, so the 2 subcatalogs, the neutrino filter and the non-neutrino filter, are then correlated in angle and in energy to the ultra-energy cosmic ray that are publicly available from Auger and telescope array. So you just have to, so this is basically the angular scan, this is the gamma ray flux scan, so we scan in 2 dimensions. You just need to concentrate on the continuous line respect the dotted line. The continuous line are the neutrino filter catalog, and the dotted line are the neutrino non-filter catalog. Okay? Here we have sources that have on top 1 or 2 or 3 neutrinos. We don't actually take into account if they are 3 or 4. The maximum actually was 4, I think. We just, again, it's 0 or 1. And interestingly enough, but it's, yeah, a hint, something that we are speculating on, once we use the second FHL and 4 years of the high energy starting events of IceCube, there is a trend that basically tell us that maybe the neutrino filter sources somehow talk a little bit to the ultra high energy cosmic ray. We see it in angle and we see it somehow in flux. Then, you know, once you're in this situation, eventually you just need to wait for more data or better catalog. And so we did that. And so we just then switched to the third FHL, which has more sources, also different thresholds, so the mixture of sources is slightly different. Again, we don't manipulate the catalog, we don't manipulate data, we just run then statistical tests. And in this case, we were getting quite excited because somehow then this minimum, so improbable scenario for the neutrino filter is then getting even more improbable or rare, which is actually what you're looking for. But then IceCube published other 2 years of data. And again, we don't manipulate all of them. And then we plug them in, and actually the significance of that drops again. So, well, we are in this state that we don't know. Of course, we are thinking about all of this, if it is a connection, where it might be, if we can improve the neutrino filter and so on. So this is work ongoing, and of course we are waiting for more data and more catalogs, and we will continue to move on that direction. All right, so I spent my last few minutes on then a smoking gun, because eventually at the end of this game, what you scream at are more data, and actually more pointing data, because to work with the showers is really a pain. But we work with shower because, as I said, these are tracing a large majority of the signal. The tracks are tracing only the muon component. But at a certain time, the muon component should start to point too. And so we were very happy, essentially, once one of the pointing events of IceCube that has been detected on the 22nd of September last year has been then broadcasted a fraction of a minute after, has been seen by Fermi, MAGIC, and other telescopes in connection to one known blazar. This known blazar is a Texas 0506 plus 056. At the beginning, none of us actually knew that object. By now, we know nearly everything, although a lot of stuff about that source are still intriguing and not obvious. That is the SED of this object. You will see a number of SEDs. This has been combined by Paolo, Giommi, and Bruno Arcioli back a few months ago with Open Universe that combines basically the broadband emission from all the existing mission. I want to then point to this fascinating work about the redshift measurement of this intermediate / high frequency blazar. As you might know, these are sources that typically are not measured in redshift because the jet is so dominant that basically destroy all the lines from the background galaxy. But Payano et al. Have been able to measure with an incredible precision the redshift. And this source is relatively far away, but I think it's getting closer to be a very first candidate for all of us. This all opens a huge amount of questions, and I don't even go through this because I know that Francis will reveal to you a little bit more, and a little bit more will be revealed next week once all the papers will be published. So something coming up very, very soon, and maybe again, the blazar, the pointing events from IceCube, in connection to the rest of the astronomy, are going to reveal a first piece of this huge puzzle that concerns cosmic accelerators. Okay, I finished stressing a very obvious point that we are at the beginning of something super exciting. It has been a long journey already, but there is a breakthrough coming up in multi-messenger astronomy. It is because there is a richness in all the messengers, and that's the main message, right? I think none of us could have been figuring out anything without a combined community, right? So there are many searches ongoing, few hints, a game changer, and there is a lot to come up soon and a lot to discover, a lot to do from the theoretical side. So it's a field that would and should, I hope, attract young, brilliant, also not that young, but any brilliant person here and around us. Of course, we are data-driven, and so we need constantly larger detector in any wavelengths from the cosmic ray point of view. We dream for even a better Fermi, but of course, personally, I dream of more neutrinos concerning ICRANet, cubic kilometer net, GVD, and maybe even new ideas. So thank you very much, and let me thanking my closer collaborators that are all here. Thank you.
Thank you very much, Elisa, also for staying perfectly on time. Interesting, very interesting talk. Are there any questions, I'm sure?
Well, the physics around black holes, we know, is similar in black holes of different masses, scales. And, the analogy of the phenomenology between supermassive and stellar mass black holes has been confirmed in several aspects of the phenomenology. So we know there are microquasars with hadrons moving at relativistic speeds. What is your expectation of detecting microblazars in our galaxy or nearby galaxies?
Well, thank you for the question. And as I said, I focus on the extragalactic sky, but IceCube is very actively searching also for galactic objects, including microquasar. So the physics is similar, although jets in blazar concern the entire dynamic of a gigantic galaxy. So it might be a little bit counterintuitive that somehow maybe the first source is an extragalactic, relatively far away object, but if this object is super bright, maybe that's it. If this is all true, of course, we keep on monitoring the microquasar. We are following some model at the level of detection to these objects too. The searches are ongoing, so we don't stop to search for them. And we, of course, dream for having multiple scenarios and many more talks to follow on also microblazar. So much more than this for the moment we don't have.
Thanks for a nice talk. I'm kind of instrumentalist, so I want to ask a nasty question. You showed this beautiful slide, which you called neutrino window. But I look into this as neutrino gap, because actually there's currently no, as much as I know, no technique which permits you to say something between the neutrinos from about 100 MeV to about 1 TeV. And a second obsession of mine, that when we started, I'm mostly dark matter business, when we started it 35 years ago, we believe that our facilities are deep enough. What we are realizing now is that our facilities are not deep enough, that we need to go to about 5 to 10 kilometers to remove all of the muons, to have a pure neutrino sample. Thank you very much.
So, first, I like obsessions. And second, your two questions are related. We can go at low energy, and IceCube in particular can go at low energy. The only thing is that there is a background, and the background is the atmospheric one. So it's always a trade-off, right, what we do. So we try, of course, to use all the background we have and search for point sources, or we we remove all the background and stay in the window of high energy and live in this window. The second point that you had is related because, indeed, to a certain extent, we use the atmospheric muons that come down together with the atmospheric neutrinos at high energy. Both are boosted in the same direction, same angle. They come down together. And so the muon at high energy from above the detector is very important to be able to tag at high energy the atmospheric neutrinos. So again, it's a trade-off between the capability to remove muon, maybe the capability to remove neutrinos. So this is what we do presently in IceCube in South at high energy, and extracting the little piece of signal that is embedded in this huge background. Okay, of course. Other? Yes, then we continue at the coffee break. Yes.
There's another question, and then we move to the next one. The last question, please.
Perhaps it would be useful to recollect to listeners tiny relation between Bruno Pontecorvo and Enrico Fermi in connection with the recent Nobel Prize to neutrino oscillations. So it was very interesting to hear this lecture, and it is very significant that we are actually at the just very close to physics department of the La Sapienza University. Thank you also.
Well, thank you for the comment, and I never, of course, met personally none of these two, but I'm pretty sure that both Pontecorvo and Enrico Fermi will be much more happy about the results than being cited. But of course, that is a piece of history that we do not forget. So, Francis, now it's you.
Thank you very much. Thank you. Thanks again.